We're finally wrapping up this 5.1, and today we're kind of hitting on why we've been using all of these identities in the first place, and it's to be able to solve some equations that have trig functions involved in them. We are going to use all of those previous identities to help us solve equations. Now, to start with, when we're solving trig equations, we want to get the equation equal to 0. And then we're going to do all those same old things like look to factor or combine like terms, isolate a trig function. What our solutions will look like will vary depending on the directions. In this case, it says find all the values of x in the interval of 0 to 2 pi. Any time or any angle that falls in that range can be our answer. Let's try a couple. As I mentioned earlier, we look to sometimes factor. If you look at this equation, you can see that you have the x squared, or the sine squared term, you have the sine linear term, and then you have a number. Let's make this equal 0, and it looks like one of those factoring problems. Remember to look at this kind of like an 2x squared plus a 1x minus 1, and how we set up the factors for that. Same deal, only instead of an x, it's going to be a sine x. I'm going to erase that so we don't run out of space. I'm going to have a 2 sine x with a 1 sine x. You don't really have to write the 1. Factors of 1 have got to be 1 and 1. One of them will be a positive, one will be a negative. Looks like I'm going to want a positive there and a negative there. You can always check. There's your outer. 2 sine x minus 1 sine x would get me this 1 sine x. It equals 0. That's what's new for us. Now it equals something. And just like with factoring, with just a regular x, oops, where did that come from? It's not secant. You're going to set each of these equal to 0 and solve them individually. On this one, I'm going to add the 1 and then divide by the 2 and end up with a sine x equals 1/2. On the left side, or on the right side, I'll just subtract the 1. And now you go to your unit circle. You're basically going to do the inverse sine function. When you see sine x equals 1/2, you do the inverse function to figure out what is the angle that would have a sine value of 1/2. Well, it happens a few times on the unit circle, but we do want it to be a positive 1/2. That means your opposite side of in your triangle, if you're thinking unit circle, how much you go up is a 1/2. That's your short leg. So that would happen there and there. Those aren't very, sorry, that's not very good, but those are your two low ones. Your pi over 6 and 5 pi over 6. Now remember what the directions said, that you're going on the interval from 0 to 2 pi. Even though we're doing that inverse and we learned that you have to always choose angles from these two quadrants, we're following what the directions say. And that will change on what we do. In this case, I want these two angles. X is going to be pi over 6 or 5 pi over 6. The other part of your answer comes from over here. What angle would have a sine value of -1? That means you're down 1. And in the range of 0 to 2 pi, that would be at 3 pi over 2. I have 3 different solutions for this problem. Fun, huh? Let's try again. Now in this example I made a typo, so you might check your notes and make sure that it's written correctly. I'm going to change this right here. It's going to read cotangent x cosecant x, or cosecant squared x equals 2 cotangent x. Yours may already be edited to that. Now, on this one, it looks like it's another one where you have a lot of trig functions in there. Let's set this equal to 0 and see if something might factor. when I bring it all over to one side, I can see here that I have on this term and this term, they both have a cotangent x. Let's factor that cotangent x out and see what's left. I have a cosecant squared x minus 2. Now I'm going to set each of those equal to 0, just like we would if we were factoring normal functions. On the left side, I'm in luck, it's already isolated. On the right side, I'm going to have a little bit of work here. I'm going to have cosecant squared x equals 2. To get rid of the squared, I'm going to have to square root both sides. Now don't forget though, when you square root both sides, that you have to put a plus or minus there. And I am not super familiar with my cosecants, so I'm going to switch that. If cosecant is the square root of 2, then sine would be plus or minus 1 over square root of 2. And that's not super familiar, but if you look at it and you rationalize it, you end up with a root 2 over 2. Okay, I'm going to have to come this way. I'm looking at when sine x would equal a plus or minus square root of 2 over 2. All right, so I've got this right here as one of mine, and this is my other one. Sine x, that's kind of messy. That's a plus equals plus or minus root 2 over 2. Now I'm going to go to my unit circle. I'm going to come up here where I have a little bit of space and think about when is cotangent 0. Well, cotangent would be 0 anytime tangent was undefined. Tangent was, remember, it was kind of like slope, so tangent was undefined here. That means that's where cotangent will be 0. Because it says in the interval from 0 to 2 pi, I start at 0 and I just make one revolution, and those are my possible answers. I'm going to have, I am going to totally, this is going to be messy, I apologize. X is going to equal pi over 2, or possibly 3 pi over 2. But I'm not done because I have this other answer that I have to be searching for also. I want all the x values where the sign is a positive or a negative root 2 over 2. Well, there's a lot of those. That's going to happen at all my 45s. And since it's positive or negative, it would be all of them. It would be this one, this one, this one, and this one. I have to list all of those. As promised, it's going to get messy. Here we go. We'll have a pi over 4. We'll have a 3 pi over 4. We're going to have a 5 pi over 4. And we're going to have a 7 pi over 4. Lots of possibilities to make this equation work. All right, let's try something else. The directions on these two examples are different. This time we're going to find all values of x, every single value that x could be. Let's start off the same way. Looks like we got a lot of trig functions. Let's go ahead and bring this sine x over to this side. And then looks like we'd have a GCF that we could factor out. There's a sine x in this term and in this one. Let's pull it out in front. Then you'll have tangent squared x minus 1. And now you set them each equal to 0, like we would in any type of factoring problem. The first one is already isolated. When is sine 0? The second one is not quite isolated. Let's add that 1 to the other side and solve. Try to isolate your tangent here. And then since it's a tangent squared x, I'll want to square root it to get rid of the squared. Don't forget that when you square root both sides, you need to put a plus or minus. End up with tangent x equals a plus or minus 1. That's a nice number off the unit circle. if we think about the unit circle, let's start with the first one. Sine x is 0. That happens, sine is going to be 0 over here and also over here. Now for them to say that they want all the values, that means I could list that as 0 and I could list it as pi, but recall that that would just continue to repeat every time I wrap around. So it would happen at 2 pi, it would happen at 3 pi, 4 pi, 5 pi, and I could sit here and list them all day long. What we do instead is we find the pattern. It appears that if we start at 0 and then every pi, we get another possible answer. My final answer then, I would say x is equal to 0, that's the first one, plus every pi, and to show that it's going to repeat, I take it times n. N just represents an integer, so it could be 1n, or n could be 1, so it'd be 1 pi. N could be 2, that'd be at 2 pi. N could be 3. We just assume the n can be any integer. It actually could be a negative number, which would work for all of the angles that worked backwards. That's how we're going to write it. Whenever it asks for all the solutions, we'll write it like a plus pi n or plus 2 pi n or something like that, depending on how often it repeats. This 0 right here is probably optional, and if you were to look like in the back of the book, they probably don't have that at all, and that's okay. Now we have to do it for the other term as well. Looking at your unit circle again, tangent is a plus or minus 1. Well, that happens at all your 45s. That would work here, and here, and here, and here. If you look at that, you're going to always list your first one, which would be pi over 4. But if it's happening at all the 45s, you can see by the graph that I've shown that it really starts repeating itself every 45 degrees. I'm going to write that x equals pi over 4, plus it will repeat, and I said 90, but we write that as pi over 2 n. Those are all the solutions that would work. Let's try another one. We have ourselves a trinomial. You got your squared term, your linear term, your constant. It's like a regular trinomial that we would try to factor. The 2 is going to be 2 sine x, and then over here we'd have a 1 sine x. Factors of 1 have to be 1 and 1. The signs are going to be the same. They'll both be pluses. And then you want to check your outer and inner real quick and make sure that gets you, there's a 2 sine x and a 1 sine x. That's how I get my 3 sine x. Now I'm going to set those each equal to 0. And then I'll solve. On the left here, I'm going to subtract the 1 and then divide by the 2. On the right, I'm just going to subtract the 1. And then I look at my unit circle and I try to figure out when does this happen. Sine x is going to be negative 1/2 right here and right here. Now, unfortunately, those are not right across from each other where you can see that it's increasing by pi. It increases by more than pi here, but less than pi here. I don't think that there's a common difference in those where I could say just list one of them plus pi n or 2 pi n. I'm going to have to list them individually. All right, x is equal to, and we do typically in our, as your first one, you pick it in the first revolution. Not counted as a negative, just call it the first one here, would be 7 pi over 6. And then I know that it would repeat, it happens there, but it would also happen there, and there, and there, every 2 pi n. For the second part, sine x is negative 1. Okay, that's going to happen straight down. X is going to end up equaling 3 pi over 2, but it would also repeat every revolution. So I'm going to add 2 pi n. And that's my other solution. Here's our last example. This one already is equal to 0. But since I only have one term, one trig term, it's not really one of the ones I'm probably going to want equal to 0. I want to isolate this term. Let's add the 1 to the other side. And then let's divide by the 3. And then I'm going to square root both sides. And this is a little bit weird. The square root of 1/3. Well, first of all, let's not forget about our plus or minus. That has to be on there. The square root of 1 is just 1 over the square root of 3. You can kind of separate that out. But if you rationalize it after you separate it, look at what we end up with. It's a square root of 3 over 3. That is something off of our unit circle. Don't forget that it's a plus or minus square root of 3 over 3. And when you go to your unit circle and you try to remember when is tangent root 3 over 3, remember our little trick that those 3's add up to 6. So it's at all the 6. That's going to happen here, 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 and here. Because it's a plus or minus, we're going to have 4 possibilities for this answer. Now, because we're looking for all the solutions, not just in a certain range from 0 to 2 pi, I have to write these in some manner that shows that it would repeat every time you wrapped around the unit circle. I could write them each individually. I could say this one plus 2 pi n, this one plus 2 pi n, this one plus 2 pi n, and this one plus 2 pi n. But you kind of look for some shortcuts and try to limit how many answers you have to list out. Since these are straight across from one another, I really could just list this one and say that it's going to occur there plus every pi n. And that would get both of those. And then I could do the same thing here. I could list this one, but because there's one straight across from it, I'll do plus pi n. Let's list them. X would have to equal, that first one was a pi over 6 plus pi n. The second one was 5 pi over 6 plus pi n.